In the first part of this tutorial, we'll be looking at integration. In machine learning, we face integration problems more or less every day. For example, if we compute moments of random variables, such as means, we need to solve an integral. Or when we want to compute the model evidence, which is useful for model comparison, we need to solve an integral. We also often need to compute Kullback-Leibler divergences, for example in variational inference. Here we also need to compute an integral. Similarly, making predictions in time series models and computing expected utilities in experimental design involves integration. Even planning, that is, computing rewards along a trajectory of states and actions, requires integration if we look at continuous time problems. We see that integration plays a central role in machine learning, but unfortunately solving integrals is hard in general. In this tutorial, we will look at different ways to compute integrals. The easiest solution to an integration problem is an analytic solution. There are books written on exactly this topic, and sometimes it's worthwhile checking this out. For example, there exist solutions to indefinite integrals of a polynomial times an unnormalized Gaussian times a trigonometric function. This can come pretty handy at times. If you can solve integrals analytically, do it. In this tutorial, I want to focus on approximate integration methods in cases when we cannot compute the value of the integral in closed form. Here's a list of topics we will cover in the next videos, including some references I found helpful while preparing this material. We will start off with numerical integration and Bayesian quadrature, which are integration techniques that work well in low and moderate dimensions. We will then go to Monte Carlo integration, which also works in high dimensions. After that, we'll have a look at normalizing flows, which allow us to compute some complicated integrals. And finally, we'll discuss techniques for inference in nonlinear time series.